Welcome. I'll be showing you our work on simultaneous wind field measurements with Doppler Lidar, Quadrotor and fixed-wing UAV. This work is a collaboration between INAC and ISAE with the authors myself Murat Bronz, Nikola Gavrilovic, Gauthier Hattenberger and Jean-Marc Mosqueta. Our main objective is to compare the feasibility of different wind measurement systems with different fidelity levels. A mobile Doppler Lidar, a fixed-wing UAV, and a small quadrotor. During our experiments, we have rented the WindCube, which is a mobile Doppler Lidar. It can measure the wind information at 20 predefined altitude levels from 40 meters up to 300 meters. The operating software provides a data sampling rate of 1 Hz. The second system includes a small fixed-wing UAV, which is a composite glider with 1.5 meter wingspan and it weighs about 1 kilogram. It is equipped with an electric motor for easy launch and recovery. We control the aircraft with an ordinary computer running Paparazzi ground control station. The telemetry is acquired by a small XP modem, and we had an RC transmitter for safety reasons. We use the well-known Paparazzi autopilot system in our work. It offers a flexible architecture, powerful flight plan language, and handles both the ground segment, airborne segment, and the post-analysis of the flights. You can find detailed information in the link below. The airspeed has been acquired with a multi-hole probe that is developed in-house at INAC. As we cannot estimate the wind speed directly, we have used an extended Kalman filter in order to estimate the wind speed indirectly. The implementation is adopted from Edwards et al., where the state matrix is selected as true airspeed and the north-east wind components. Using the onboard GPS measurements and the wind triangle, we can define an error measure, epsilon, which we drive to 0 during update stage. As an augmentation to the first filter, we can add airspeed norm and define the measurement matrix as Z and modify the observation model Hx. The Jacobian matrix of the observation model becomes as equation 8, and then we just need to modify the update stage of the filter as shown to finalize our second method. As a third method, we went back to using only GPS information again, but this time we project the GPS vector to Cartesian plane as shown in the middle image. Each red dot representing one measurement here. And then by using a minimization algorithm, we fit a circle around these measurement points. The resultant radius reveals the airspeed norm and the center location defines the wind information. As it can be seen, this method assumes a constant airspeed during the flight. Actually, we can augment this method further by relaxing this assumption and adding the airspeed norm to the minimization algorithm during the fitting process. Theoretically, this should increase the possibility of capturing the wind variations. As a third system, we used a simple quadrotor flying fully autonomously with Paparazzi autopilot. During stationary flight, its inclination angle reveals the drag force, hence the applied wind speed information. This relation needs to be calibrated in front of a wind tunnel or from a predefined flight pattern in calm weather. Here you can see INAC's indoor flight arena and the wind-shaped machine used as a mobile wind tunnel in order to calibrate the quadrotor during free flight. Not attached to the ground. The presented system collects and stores data in 5 different locations. The low frequency data is logged under the ground control station computer. A high frequency log is stored inside the SD card of the autopilot. Smart Probe also logs the sensory data on board its own SD card at 500 Hz. Mobile LiDAR logs are the wind vectors for different altitudes reconstructed at 1 Hz, and the Quadrotor flight logs, including its full state at 10 Hz, are located also in the ground control station computer. Now let's look at the measurement results. Doppler Lidar offers us a very accurate measurements. Here we can see the vertical velocity profiles measured every 4 seconds in the first, every 6 minutes in the second, and averaged over 30 minutes of sampling on the third image. What catches the eye is the huge variance. However, once we average over a period of time, a nice stable vertical profile is visible. And we think that the LiDAR is very suitable for that. In order to validate the other methods, we first flew the Quadrotor from ground up to 100 meters and down. Then we flew the fixed-wing aircraft from 150 meters to the ground, and then we have repeated the Quadrotor flight once more. The two climb and descents of the Quadrotor is visible here. Applying the proposed method to the total inclination angle of the Quadrotor, now we can estimate the wind speed. In these figures, you can see the climb and descent phase of the Quadrotor alongside with the synchronized Doppler Lidar data. A close coherence is visible in both flights, ensuring that this cheap solution can be very useful for most of the real-life applications. Finally, you can see the flight profile of the fixed-wing UAV, first climbing up to 150 meters and then circling down with 0.5 meter per second vertical speed at 16.5 meter per second constant airspeed. These figures shows the estimated wind speed with 4 different methods as introduced in the previous section alongside with altitude and time synchronized Doppler Lidar data. Small altitude variations during the descent generate noisy results, unfortunately. However, the global structure is captured in both 4 methods. On the other side, the global optimization method with or without the airspeed norm show a better coherence compared to the Doppler Lidar data. A probable reason for this can be that the global optimization method uses a longer time sequence of measurements to estimate the wind speed. The rolling sample range has been selected to correspond approximately to 1 full circle, which is about 450 samples on average. The augmented global optimization doesn't show a significant difference compared to GPS-only optimization. Most probably, during the test flights, the airspeed was actively controlled and stabilized at 16.5 meters per second very precisely. However, the introduction of the airspeed norm to the extended Kalman filter as an augmentation delayed the convergence in our experiences. We need further analysis to discuss this behavior. As a conclusion, we compared the feasible measurement accuracy between 3 different systems which are representing different fidelity levels. Doppler Lidar is the most accurate but also the most expensive from the cost and also the logistic point of view. The fixed-wing UAV presents a cheaper and more flexible measurement opportunity despite its operational complexity. However, it will be the most suitable method for high-altitude measurements for sure. Finally, the Quadrotor-based system offers a very agile operation in cheap hardware with a small compromise in measurement accuracy, especially for low altitude and close-range flights. It also offers stationary flight possibility, which can be used for fixed-point averaged measurements. Additionally, the system is very suitable for multi-vehicle operations where a fleet of Quadrotors can measure a volume for wind field estimations. Our future work will be on validating the effect of variable airspeed norm augmentation on the global optimization method and also preparing the fleet of Quadrotors to study the possibility of wind speed measurements over a larger volume in a synchronized manner. Thank you very much for your attention and please check out our webpage for the data and the post-processing code.